All right, so now we're going to apply the idea of limits to sequences. So here's a sequence, a sub n is 1 over n, so that's going to be 1, 1/2, 1/3, 1/4. And it's pretty obvious where these values are going, right? They're going to 0. So, there's nothing mind-boggling about that. The limit as n approaches infinity of this sequence 1 over n is equal to 0. That's how we can write that. And it really, to justify this, you would just say the numerator is bounded while the denominator increases without bound. Therefore, the limit is 0. All right? So that's what's going on with limits. But I'm going to show you this one time, just one time. Limits always come back to epsilon, and the distance of the function value, which in this case is a sub n, from the limit, which in this case is 0, being within epsilon under certain conditions. There's no delta here, so we're saying that for every epsilon greater than 0, there exists a natural number m, so that's the number in the domain, so that's like the delta, so that if n is greater than m, then the function values are within epsilon of the limit. So I'm just going to show you one time how that works, and you don't have to be too you don't have to understand it too well, but it's good to at least see it once. So why is this limit 0? It goes like this. For every epsilon greater than 0, there is a real natural number m, which, by the way, depends on epsilon, such that if n, the index variable, so which one you're on, is past that value of m, in other words, there's an m somewhere that if I go past that index value, then from then on, the distance from a sub n to the limit is less than epsilon. All right? So for this particular limit, it's actually easy to see what that value is. The m for every epsilon is equal to 1 over epsilon. So because what happens then is if n is greater than m, which is equal to 1 over epsilon, then what happens? What happens with a sub n minus L, right? The absolute value of a sub n minus L. Well, that's equal to our a sub n is 1 over n and our L is 0. Our purported limit is 0. And that just equals 1 over n because 1 over n minus 0 is 0, and the 1 over n's, these values are all positive, so we don't need the absolute value. All right? And that 1 over n, in fact, is less than 1 over epsilon. So how this works is let's put it this way. 1 over epsilon is less than n. So if I replace the n with 1 over epsilon, a smaller number in the denominator, the fraction as a whole becomes larger. All right? And this 1 over epsilon is just equal to epsilon. All right? So here's what we've got here, putting this together. The absolute value of a sub n minus L is less than epsilon. As long as n is greater than m, it follows as an algebraic consequence, the absolute value of a sub n minus L is less than epsilon. So how does that work with some sort of specific numbers? Like what if epsilon equals 1/10? All right, what would n be? So I would need to have n be greater than 1 over epsilon. So 1 over epsilon is 10. So if I take n equals 11, right? Then what's I should call it a sub 11. What's a sub 11? Well, it's 1/11, and that's less than our epsilon, which is 1/10. Right, and in fact, this sequence is decreasing, so all of the a sub n's past that. So for all n greater than m, so for n greater than 11, no matter what it is, the a sub n is going to be less than 1/10, because it's going to be less than this value. The function is decreasing. What if I have epsilon equals 1/100th? See, that's how the epsilon works. I take smaller and smaller values. Right, then what would I need n to be? Always have, I want m to be 1 over epsilon and n to be greater than that. So for n greater than 101, right, I have a sub 101 is equal to 1 over 101, and that's less than 1/100th, less than the epsilon. And in fact, any n greater than 101, a sub n is going to be less than 1/100th, because these a sub n's are just getting smaller. All right, so that's, sort of generally how this works, and I wanted to just sort of run through this definition, the epsilon definition of the limit of a sequence. We'll never have to do that again, but I just wanted to show it to you so that you know it's there when you come to your advanced calculus class. And by the way, all of these different limit definitions, there are many different kinds of limit definitions, and I've collected them all together on a paper called Epsilon Definitions of the Limit or something, Definitions of the Limit. It's posted on the website, and I think I'll repost it with this set of videos. Okay, so next up, we're going to look at some other specific limits, limits of what sequences are. It's very easy to do. You don't have to do all this. You're just going to use your knowledge of limits of functions.